Oh, I just realized, I already saved the video and uploaded it to YouTube, and I just realized I forgot to cover the stuff at the bottom, which is going to become really important to us. We have certain standard ways to represent different atoms by color. So red, like in this picture, always means oxygen. White means hydrogen. So H2O is shown 1 oxygen, 2 hydrogens, just like so. Okay, so this is going to come up when we do an experiment later in the semester. We're going to give you some model kits. Oh, come on, focus. That allow you to build these molecules in 3 dimensions, so you can see what they, more accurately anyway, what they look like. So of course, a piece of paper cannot portray physical matter correctly because there's only 2 dimensions, and matter works in 3 dimensions. Okay, so like this is water, of course, H2O. The chemical name for that is dihydrogen monoxide. Sounds scary, but isn't. And of course, this is a different molecule. It's really common, right? And we have 2 double bonds on this one. You can see them both if I turn it kind of sideways, but take a second and pause the video and see if you can tell what the chemical formula of this is just based on the color. Did you get CO2? I hope so. This is carbon dioxide. It's my daughter's favorite molecule. I don't know why, but she likes it. So I have to make a lot of these. She likes to play with them. Don't worry, you'll get your chance to play with the modeling kit later in the semester. Okay, so moving on to the next topic. We said before, if you have a metal and a nonmetal together, you're going to get an ionic bond. That's a pretty loose, not metal. That's a pretty loose definition, actually, and it's not as clear-cut as it initially sounds, but when we name things, we accept that as the definition of ionic. We're going to learn when we get to bonding later on in the semester. We're going to bond. When we get to bonding later in the semester, we're going to learn about a quantitative way to determine when things are ionic or covalent, meaning there's numbers. But instead, for now, you'll just remember the areas of the periodic table, and if you see a compound where a metal and a nonmetal are connected to each other, you know that that's ionic, and you're going to follow the rules for naming ionic things. On the other hand, we said covalent compounds are when you have a nonmetal bonded to a nonmetal, right? So that's just things in the upper right corner of the periodic table. So it's important to understand, I'm going to move my picture so we can see the slide. It's important to understand what an ionic bond means, okay? It's between ions. So we talked about ions in terms of forming from elements by giving up or adding electrons, depending which side of the periodic table they fall on. Metals tend to give up electrons, and nonmetals tend to take them. So metals tend to be positive ions, and nonmetals tend to be negative. So we have names for those things, right? So I just said metals tend to be positive. Okay, and nonmetals are negative. And so we have a name for positive ions, and it's a cation. So there's 2 ways to remember this one. You can just remember that there's a big T in the middle, which looks like a plus sign. So cations are the positive ones, usually metals, although there's a few other examples too. Nonmetals tend to be negative, and so we have a word for them as well. We call those anions. There's no clever way to remember that sort of phrase. You just, or at least not one that I know of. If you find one, share it. All right, but cations are positive. They're usually the metal, and anions are negative. They're typically the nonmetal. Okay. As it turns out, when an element picks up an extra electron, so to become negative, it picks up an electron, it's an anion at that point, it will get bigger. That makes sense because most of the volume of an atom is due to the number of electrons that it has. On the other hand, when a cation loses an electron, it shrinks. So positively charged things are smaller than their neutral what we call parent atoms. So like sodium. When sodium loses, so this is the element, there's no charge. When it becomes the ion, Na+, it gave up an electron to do that, so it shrank. Na+ is smaller than Na. Ionic compounds exist as really geometrically organized solids. Okay, so when you think about this, you're thinking about things like salt. If you look closely at salt, it's a cube. Sugar, also crystalline, right? So they have a repeating pattern. The benzoic acid from the beginning of the semester, if you purified it well, was crystalline as well. So they look kind of sparkly. They have defined shapes to them. That's different than nonmetal compounds, which tend to be kind of powdery and not as sparkly, if you will. So you should be able to take this periodic table from the notes and use a highlighter to color in the 3 sections: metals, nonmetals, and metalloids in different colors. You should also label the important group names, such as the alkali metals, group 1, alkaline earth metals, group 2. Groups 3 through 12 are usually called transition metals. The groups down here in the bottom, this is called the lanthanide series because it belongs between lanthanum and hafnium. So this whole row, whoopsie, that whole row stuck down on the bottom that starts at 58 and ends at 71 goes in between these 2 elements. Okay. We don't write that way because it doesn't fit on a periodic table very well, on a paper very well. And then we call this bottom row here the actinide series because it's between actinium and whatever RF is. I don't remember. We don't see it very often. It's man-made and it's very, very rare. So anyway, thorium and all the rest of these fit in between these 2 elements. So you can just follow along with the atomic numbers if you get lost. But anyway, this is the lanthanide series. That's the actinide series. And the middle bit, 3 through 12, that is the transition metals. And then, of course, the noble gases are all the way over here. Do you know why they call them noble gases? Because they don't do anything. Get it? Nobles don't do anything? Get it? Yeah, okay. All right. And then we have group 17, which is called halogens or halides. Those 2 terms are used interchangeably. And I think that's about it. That's pretty good. So if you can label your periodic table of all those things, maybe print it a couple times, practice that, because we use those phrases to refer to the different elements all the time. Oh, one other thing I should review. Just a reminder, the groups are the vertical ones. So there's 18 groups, 1 through 18. And the horizontal ones are called periods. Okay, so groups are all arranged because in the same group because they react the same. They used to be called families. So everybody in the same family has a tendency to do the same thing when exposed to a given thing. So like group 1 always catches on fire in water, which is kind of unique. It's why they don't exist in nature, like ever. Okay. Anyway, so originally the periodic table was organized by reactivity, and it wasn't until many years later, in 1911, when we discovered what protons are, and we realized that as you go up the periodic table, you gain 1 proton in every box, right? And so that's what the atomic number shows you. Don't tell me the periodic table was originally organized by atomic number, because that is literally 70, what, 40 years, 20 years apart? I don't know. A bunch of years apart. Okay, so it's not possible. Anyway, so you should be able to name those groups in the periodic table. All right, so this is a picture of salt on the particle level, so sodium chloride, all right? This is not an I, that's an L. I's look like this. That's an L. Also worth noting, first letter of an element is always capitalized, second letter is always lowercase if there is one. So this is 2 different elements. Na is one of them, sodium, and Cl. And if you don't recognize those symbols yet, you need to make some flashcards of the elements because naming is much harder if you don't know the name of the elements in question. So start there. And then come back and watch videos about naming. All right, so here, oh, I got my colors backwards actually. I just noticed. So The green one is slightly bigger than the purple. And I just said that metals like to become positive and nonmetals like to become negative. And I also said when things become positive, they shrink because they are giving up electrons. So that means the chlorine is the one that got bigger and the sodium is the one that got smaller. Oh, there we go. That's better. So anyways, this is a sodium. That's a chlorine. All right, but when we think about ionic formulas, they're a representation of the ratio. So if you felt like counting all of the green ones in this cube and all of the purple ones in this cube, you'd end up with the same exact number for both of them. Okay, and that's what you're showing. This is the empirical formula of an ionic solid. We don't ever show like total number of NAs in a crystal because it varies depending on the size of the crystal. You could make a big piece of sodium chloride and it would be a lot of atoms to count. So when we have ionic substances, we just make a ratio instead. And this ball and stick diagram is showing you essentially the same thing. Crystalline means geometric shape. So cube is one of them, and there are many more. So, what you need to do here is identify what is ionic and what is covalent. So like I said, we're working towards getting to naming, and you can't name things if you don't know which one's covalent or which one's ionic, because we have different ways to do it for each of those. So pause the video, make a guess on each one of these, and then resume. I feel like I need hold music or something to give you just a second to hit the pause button. Okay, this one is interesting because it's actually covalent and ionic. So we have some special groups called polyatomic ions. And on the periodic table that I believe you got in lab, you did if you're in my lab, if you didn't, ask your professor. They're in the labs. It's green and it's cardstock. And on the back of it is a list of polyatomic ions that you need to know. You should memorize them. It makes naming much faster. Polyatomic ions are always covalent bonds, all of them. But when this negative ion attaches to the calcium, that's an ionic bond. So you can have both types in one compound, okay? Be on the lookout for that. We're going to see it a lot. All right, so over here we have mercury, which is a metal, and chlorine, which is a nonmetal, so we're going to call that one ionic. Over here, we'll come back to that one. PF5 is covalent because phosphorus and fluorine are in the upper right corner of the periodic table. We do expect you to recognize phosphorus and fluorine. Again, flashcards are good. Here we have Ag, which is a metal, silver, and chlorine. We should recognize those two elements also. So silver and chlorine, that's ionic because we have a metal and a nonmetal. Carbon dioxide is covalent because they both hang out in the upper right corner of the periodic table. This is copper, and this is called nitrate. It's another polyatomic. So again, that's going to be covalent, but the copper to nitrate bond is the ionic part. This is not glucose. Glucose. Now it's glucose. I don't know why that's a 2. I don't know what. That's not a real structure. That's probably a typo. Anyways, I fixed it. So this is glucose, C6H12O6, and that's covalent because all of those, carbon, hydrogen, and oxygen, are nonmetals. This very friendly molecule, HI, is hydrogen and iodine, which are both nonmetals, so it's covalent. And this one's special because usually when you have an H in the front, if it also says aqueous, it's probably an acid. Oh, lovely. Okay, so the one we skipped, okay, this is my favorite molecule in the entire universe. It's an anti-cancer drug, one of the first ever invented. And just like to give you a structural drawing, it looks like this. Those are chlorines attached to a platinum, and then they have NH3, which looks like this. There's 2 different ways this can be arranged. I'm just going to collect that together because I don't want to draw all the H's separately.